Have you ever wondered how the mass of a rotating body is distributed around its axis? Why does a thin rod spin differently from a solid disk, even if they have the same mass? The answer lies in a single concept: the radius of gyration. Let's dive in and decode this powerful term in rotational mechanics. The radius of gyration, symbolized by K, is a measure of how mass is distributed about an axis of rotation. It's defined as the distance from the axis of rotation to a point where the entire mass of the body can be assumed to be concentrated without changing its moment of inertia. In simple terms, it's a virtual distance that tells us how spread out the mass is while the body rotates. Mathematically, the moment of inertia, I, of a body is related to the radius of gyration by the equation. I is equals to m multiplied by k square, where m is the total mass of the body and k is the radius of gyration. From this, we can find that k is equals to the square root of the ratio of moment of inertia, y, to mass m. It has the unit of meters and dimensions of length, that is m0, l1, t0. Thus, the radius of gyration doesn't represent mass or inertia directly. It represents how far that inertia effectively acts. Physical meaning. Think of the radius of gyration as a way to simplify complex shapes. Imagine replacing a solid body with a single point mass that's located at a distance k from the axis, such that it spins with the same moment of inertia as the actual body. That's the essence of the radius of gyration, a conceptual shortcut to understand rotational dynamics. Let's understand it with an example. Suppose a body has a moment of inertia I of 360 kg/m² and a mass m of 10 kilograms. Using the formula K is equals to square root of I divided by m. K square is equals to 360 divided by 10. K square is equals to 36. Therefore, K is equals to 6 meters. That means the body behaves as if its entire 10 kilograms mass were concentrated 6 meters away from the axis, producing the same rotational effect. Notice what happens as the mass spreads farther from the axis. The radius of gyration increases, and so does the moment of inertia. This is why a skater spins faster when they pull their arms in. They reduce their radius of gyration and hence their moment of inertia. So, the radius of gyration is the bridge between mass distribution and rotational speed. Multiple choice practice. Let's test your understanding. Question 1. The radius of gyration for a body with I is equals to 50 kg/m² and m is equals to 10 kilograms is A, 5 meters, B, 0.5 meters, C, 50 meters, D, 500 meters. The correct answer is 5 meters. Question 2. If the entire mass of a body were concentrated at one point producing the same moment of inertia, that distance is called A, radius of rotation, B, radius of gyration, C, radius of wheel, D, radius of whirl. The correct answer, radius of gyration. And finally, question 3. For K is equals to 5 meters and M is equals to 10 kilograms, what's the moment of inertia? Answer will be, as I is equals to M multiplied by K square is equals to 10 multiplied by 25 is equals to 250 kg/m². Let's recap what we've learned. Radius of gyration, K, tells us how far the mass of a rotating body is effectively located from the axis of rotation. It simplifies complex rotational systems, relates directly to moment of inertia through I is equals to M multiplied by K square, and carries the unit of meters. Understanding it helps engineers, physicists, and designers optimize the balance and stability of rotating systems. from flywheels to satellites. So the next time you see a spinning object, from a ballerina to a turbine, remember, it's not just spinning, it's revealing the story of its radius of gyration. Thank you for watching, and keep exploring the physics behind motion.